Testing. Hello, everybody. It's just me. Oh. Good morning. It's like you didn't anyone here. It's just about 8 o'clock. Can you hear me? Hello? All right, let me try this again. I need to let's see, Kyle. All right. Kyle, can you hear me?
Yeah.
Oh, good. All right, thank you. All right. It's good. I was just about to just about to hop out. There was no, basically there was only one person there, and but that one person couldn't hear me, and I thought, oh no. All right. Whoops, let's not go back there. And yeah, well, let's get started. Okay. As you can see, I'm trying this from another location, so we'll see how this goes. All right, but everybody can hear me, so that's good. We'll get started here. All right. So the other day we were talking about these kinds of problems where we were trying to determine the pKa or possibly the pKb of a base. So the pKa for an acid or the pKb for a base. So there's a couple of things we're going to do here. We're going to go through, first of all, how to write the equations that involve acids and bases. And then we're also going to look at the kinds of problems that you might see coming up on the test here, so that we can classify and make sure that we understand exactly what we have to do in each situation. Let's first of all focus on the first step here with the acids. So what I'm going to do is I'm going to show you with regard to this particular example. Let me put you all down. Oh, here we go. That's better. Put you all down here. All right. So when we're talking about acids, so we've got HF here. We know that if for Ka, and I'll write Ka here, that HF will split into H plus, and then whatever else is with it, F minus. Now the alternative to writing it this way is to do this, is to go HF plus water, and that gives H3O plus F minus. So either way is actually legal for separating out an acid. And the reason for that is because H plus and H3O plus are equivalent statements. All H3O plus is H2O with an H plus connected to it if you look at it. I mean, I can draw a structure of it. It looks like this. So this is the Lewis structure for H3O plus, but really all it is water with an H plus connected to it. Because in reality, that's what H3O plus is. It's going to be the just H2O with an H plus attached to it. Now, when we're dealing with HF going to H plus and F minus, the assumption is that it's in water anyway, and we're just ignoring the water because we can do that. Now the KB, let me show you, go back to the example we did the other day for the KB. For the KB, I have no choice. I have to do CH3 NH2 plus water. And the reason for that is because I know that I'm forming OH minus, and with it I'll have the conjugate acid, which would be CH3 NH3 plus. So what I do here is I sort of think of the water as being effectively H plus and OH minus. So your OH minus ends up here, and the H plus ends up being joined to whatever else you've got over here. So it's not really that bad when you're writing out the equations. So either way, on the acids, we can either add water or not add water. But if we do add water, then we're going to have H3O plus as a product. And if we don't add water, then it will just be H plus. But either way is fine for the acids. But for the bases, we don't have a choice. We have to add water every single time. I'm going to stop here for a second. Does anybody have any questions? All right, nobody's saying anything, so I'm going to assume that you're okay. Let's go to the Let's go to the test here, and we'll look at some problems of how to come up with. Whoops, sorry about that. I need to move it. You are not. It's not being very. It's not being very cooperative here. Hang on. Let's put it up here. All right, we'll try that for now. Zoom thinks it's cleverer than I am. Well, I got news for Zoom. Okay. So let's look at the test questions here that relate to coming up with the equations. And the ones we're talking about here would be, here we go, questions 8 and 9. All right, so here's what it says. It says, what are the products of this equation when related to Ka? You'll notice that in order to remove any doubt about what's going on, I've added water into the equation here. So we know that we're going to get H3O plus here as a product because I've added in the water. And you'll notice for the base, I've done the same thing. I've added water as well. All right, so we know what we're getting in each case here. Let's look at the, let me move this over here a little bit. Okay, I'll get rid of this. I'll put this down here. Maybe. There we go. Yeah, so let's look at the actual equations we have. We have CH3 2pH plus H2O. See how we handle that. Whoops. So if it's going to be Ka, and that's what it says here, we know that we're going to get acid as a product. Now that acid will be H3O plus. And the rest of it here will be CH3 2 and it'll be P minus. So you'll notice that the charge will go down by 1 and we lose an H. So we lose H plus. All right, so minus H. Let's not do that. That might be a little bit too annoying to say that. So we lose H. Charge goes down by 1. Now, I'm hoping that makes sense. Does anybody have any questions? And what I mean by that is I'm looking over here at the product, the CH3 2P minus. Let's look at another example. Let's say it was something like this. All right, so we know we'd be getting H3O plus as a product here. Can anybody tell me what the other product would be? Can anybody tell me what the other product would be?
I'll give it a shot. Is it CH3 2 PH3 with a neutral charge?
No.
No. Okay.
It'd be
Oh no, I lost the H. It's P. It's just PH, right?
PH. There we go.
Okay, I added
That's right.
one.
Yeah, that's right. You see, the thing is that what's happened here is that this is effectively, well, we're losing the H plus from here, which means that we're losing an H and a positive charge. You'll also notice that the charges match here. We're going to have 1 plus total on this side and 1 plus total on this side. In the previous example, that was 0. And when we have plus and minus together, of course, that's 0 as well. So the charges do match on each side. Does anybody have any questions? All right, so that's an example there. Let's look at this situation here. Now it says KB, and that's your signal that we're dealing with base here. So let's have a look. We've got CH3, pH2, plus water. Now I know I'm getting OH minus as a product here. And what's going to happen here is I consider the water to be like H plus and OH minus. So the OH minus is already up here. And the H plus here will join with this creature, and we'll end up getting CH3, pH3 with a plus on it. Does anybody have any questions? I can't believe nobody has any questions. Surely, come on.
How do you know if it's going to turn into OH or H3?
Okay, now we get that from the problem. See how this says KB?
KB?
Yeah, now B means base, and base means OH minus, right?
Oh, okay.
Okay, now Alex, right? Is that right? All I can see is your initials.
Yeah.
Okay, now look at the previous example. What do we have here? Ka. What's the A for? The A is for acid. That's H plus. Or in this case, H3O plus. You with me?
Yeah.
Okay. All right, let's ramp this up a little bit. Let me show you another example. Let's say we had, well, let's see, HPO4 2 minus plus water. And again, we're talking about KB, and let me be real clear about this. And B is for base, of course. So we're getting OH minus. Can anybody tell me what the other species would be?
H2PO4 2 minus?
Well,
No, 2. Minus 1.
Minus 1, yeah, that's it. That's right. Good job. There we go. Now, as you can see here, what's happened is that again we take the H2O, we split it up into H plus and OH minus. The OH minus ends up over here. The H plus ends up being added up here to the HPO4 2 minus. But what that does is it increases the number of hydrogens by 1, of course, but it also sends the charge up by 1 from 2 minus up to -1. And again, if you look at the balancing here, we've got -2, and then we've got -2 over here as well. Does anybody have any questions? let's re-roll this and we'll look at a couple of other examples here. Because, well, you know, it's one of those things, you just want to practice it so you can see the pattern. See how it's the preview here. Let's keep this going. Here we go. It's not being very cooperative. Okay. Why don't you all try this one? Just see if you can come up with it on your own. Now it says KA for this one, and then you can, then for kicks, you can try this one, the KB. So the top one's for KA, the second one is for KB. I know I've chopped up the top of the question there, but okay, so that's for KA. And the other one is KB, and that's going to be pH, NH negative plus water. Okay. I wish this would be more cooperative about moving this. It's really annoying. I don't know why it does this. It just will not seem, it just will not. There we go. So what I want to do here is I'll make this CH3SH2 plus. Oh, sorry. No, I'm lying here. Sorry. Let's try again. Because it's Ka, it's H3O plus. Sorry. Plus CH3S minus is what you should have on the Ka. And on the Kb, it should be we'll do OH minus first. And then pH NH2 will be the answer there. Does anybody have any questions? So that's what I would recommend. Practice them. Practice 8 and 9. I mean, just do them again and again and again and again and again and again and again until you understand what you're doing, and you'll be fine with it. I mean, generally speaking, people hate this question on the test, but there's no real need to. I mean, it's one they just say, well, look, I'm never going to understand this. But it doesn't have to be that way. It really doesn't. I think you'll be okay with it. Okay. Okay, I've lost this again now. All right. I'm going to have to sort out how this bloody thing works. Let's do that. All right. Oh dear. All right. I still don't like that though. Okay. See if that's any better. I don't know. We'll leave it like that for now. I don't like not seeing anybody. That's kind of annoying. All right, let's have a look at the other problems that we have here. So for questions 10 and 11, there are actually 4 possibilities that could happen here. You can be looking for and we could be looking for KA and we're given, in this case, we could be given PH, or we can be looking for KA and be given POH. All right, so now for KB, it's the same situation. We could be given PH, or KB, we could be given POH. I'll put another column in here and we'll see what we need. So in the case of Ka, we need H plus. In the case of Ka, we still need H plus. For Kb, we need OH minus. And this last column here is subtract from 14. So in the case of Ka, we're given pH, we need H plus, so we don't need to do a subtraction from 14. If we're looking for Ka, we're given POH, we still need H plus, so we do need to do a subtraction from 14. In the case of Kb, we need OH minus, but we're given pH, so we would need to do a subtraction from 14. If we're looking for Kb, we're given POH, we need OH minus, we wouldn't need to do a subtraction from 14. So what I mean by subtraction from 14, for the case of the Ka there, it would mean that the pH could be obtained by taking 14 minus the POH. Now, we talked about this last time. And in the case of the Kb, we'd need the POH, and that would mean that it would be 14 minus the pH. All right, so that's kind of important because you're going to get 2 problems in number 10 and 11, and it could be any of those 4 that you're seeing there. So any of those combinations, you need to be able to handle any of those different combinations of either Ka and pH, Ka, POH, Kb and pH, or Kb and POH. And in each instance, you need to be aware of what you're doing here. So I'm going to do number 10 and 11 here. And I'm going to leave this up. I'll go ahead and get a new window here. Okay. So I can come back and reference that. All right, it says calculate the Ka of a 0.81 molar solution of XH that has POH of 12.2. Okay. So let's have a look at how we handle that. We've got our XH. Now, just to be consistent with what I had earlier, I'm going to go ahead and add water, but I don't have to add water to this because it is a Ka. So I'll add H2O plus XH. And we'll get H3O plus, and remember this is Ka, H3O plus X minus. Does anybody have any questions so far? The other option, which I'll put up here, which is quite legal as well, would be just to have XH go to H plus and X minus, which would be fine. Now, initially, is the initial molarity, we got XH as being 0.81 molar, and the H plus and the X minus will both be 0. The equilibrium would be 0.81 minus Z, and Z. Does anybody have any questions so far? Now, if you look at what we're given POH. Now, so going back to my previous example here, sorry, my previous screen. What you can see is when we're looking for Ka and we're given POH, we need the H plus because it is Ka, which means we will have to subtract from 14. But my point is you don't always subtract from 14. You only do it when you need to. So in this case, I need the H plus, and what I have is the POH. So the POH is 12.2. So the pH is going to be 14 minus the POH, which is going to be 14 minus 12.2, which is going to be 1.8. So that gives me the pH. Now the concentration of H plus, which is what we need for the problem, which is also, I'll point out, the concentration of H3O plus is the same thing, is going to be 10 to the negative pH, which is 10 to the negative 1.8. So when I do that, let's have a look. And let's see. I get 0.016. Two significant figures there. All right, I'm going to stop here for a second. Is anybody uncertain about why I'm doing this subtraction from 14 here? Okay. Understand that if you were given pH and not POH, you wouldn't do this subtraction. All right, that's what I'm trying to get at, because pH gives you H plus directly. POH would lead to OH minus. So that's why we need to be sure about what we're doing here. Now we know that for the Ka, it's going to be the concentration of H3O plus times x minus over xh. Remember, we ignore the water here. The water is a constant concentration. So that's going to be z squared over 0.81 minus z. And z squared is going to be 0.016 because that is the concentration of H plus as well. So that equals z. I'll go ahead and put that in there. And that's over 0.81 minus 0.016. Now, for the sake of significant figures, I am going to have to do that subtraction first and apply significant figure rules to that. And that's going to be 0.79. Now, the way that works is we've got 0.81, that's 2 places past the decimal, and then we've got 0.016, which is 3 places past the decimal. When I put that into my calculator, I get 0.794, which rounds down to 0.79. Does anybody have any questions? So then that gives us our final answer here. And it would be, let's see, 0.016 squared divided by 0.79. And I get 3.2 times 10 to the negative 4. And it's asking for an answer to 3 significant figures here. But really, I suppose it would only be 2. But it's not going to really matter because it's a... it won't matter because it's going to have a tolerance attached to it anyway. So it will just... But just to obey what's going on here, I'll do that 0.000324. So you don't express this as a, you know, express it as an exponent. You just express it with decimals, and that'll give you your answer. Does anybody have any questions? I probably should change those problems and make them pKa's, but I think it's probably going to be better just to keep it this way for now. All right, anybody got any questions at all?
So you only subtract from 14 when it's POH?
Well, when
Or...
no, Sondus, is that you who's asking?
No, that was me.
Georgiana. Oh, Georgiana, sorry. It depends, Georgiana. If you're looking for Ka and you're given POH, then yes, you do need to do that.
Okay.
If you're looking for KB and you're given pH, you need to do it as well.
Okay, that makes sense now.
Okay. But you have to understand why you're doing that. You know, that's really key. All right, let's look at the next one here. And it says calculate the Kb of a solution of X that has a pOH of 1.6. Okay. Now this is Kb, which means we definitely know we're going to need H plus, sorry, OH minus, OH minus. And that's why we're adding in the water. So we get OH minus, and the other species that we get as a result of that will be XH plus. Now the initial is going to be 0.58 and 0 and 0. And then on the equilibrium, it'll be 0.58 minus Z, Z and Z. And then we need the OH minus, but look what we're given. We're given POH. So from there, I'm hoping that you can see we don't need to do this subtraction from 14. Do you see that, Georgiana?
Yeah, I see it. I
Okay,
see
good.
it from the
Okay,
table
good.
you made.
That's good. All right, good. So if we've got POH as being 1.6, then the concentration of OH minus, then we can get directly, and it's going to be 10 to the negative POH. So no subtraction in this case. And that means it's 10 to the negative 1.6. And I get 0.025. And that's going to be my Z value as well, because concentration of OH minus at equilibrium is Z. And we can see that there. So the KB then is going to be OH minus times XH plus over X. And that's going to be Z squared over 0.58 minus Z. And Z squared is going to be 0.025 squared over 0.58 minus 0.025, which again would necessitate me having to figure out the significant figures. And that would be, let's see, 0.55. See, when I put that into my calculator, I'm going to get 0.5, let's see, 0.55, let me see, make sure I get this right. Yeah, 0.555, actually, it should be 0.56 is what I'm going to have to put in here. Yeah, so that'd be 0.56, and then that'll give me my answer. So 0.56 divided, sorry, 0.025 squared divided by 0.56. And I'm going to get 0.00111 as my answer. No, 112. And that will be my final answer for KB. Does anybody have any questions? So you need to understand that questions 10 and 11 can be any combinations from this table. You can have Ka and be given pH, Ka and be given POH, Kb and be given pH, or Kb and be given POH. And you have to be aware then of which what you're going to have to do to get what you need at the end. And it all depends on what you're given and what you want. And Ka will always need H plus, so we in the end we need pH. For Kb, where we need OH minus, so in the end we need POH. All right, does anybody have any questions at all about any of that? Okay, all right, so as long as everybody's clear on this, we'll move on to the next part. All right, so what we're going to look at now is how to calculate the concentration of species in solution if we're given the Ka. Up to this point, we've been looking for the Ka or looking for the Kb. Now we're going to take this to a different place, and we're going to say, well, what if you're given the Ka? Can we figure out the concentration of species in solution at that point? And the answer is yes, you can. So let's look at an example of that. And the example I'm giving you here, it says calculate HCNO, H3O plus, and CNO minus from a solution of 0.184 molar HCNO. So I'll just do it as I have it here. So we've got H2O plus HCNO. Now you don't have to do the H2O if you don't want to, because we are dealing with Ka, so whoops, it's H3O plus CNO minus. So the setup is very similar to what we were just dealing with. So we're going to have 0.184 initially as the concentration of the HCNO, and everything else is going to be zero. The product's going to be zero. Then at equilibrium, this is going to split apart, and we're going to have 0.184 minus Z and Z. Z and Z is the concentrations of the H3O plus and CNO minus products. Anybody have any questions so far? So we do have the Ka equation here that we can come up with. We are given the Ka in the problem. You can see it's 3.46 times 10 to the negative 4. So, you know, theoretically, we should be able to solve for these equilibrium concentrations. We're effectively solving for Z. But there's our Ka expression there. Let's look at the next slide. So if I sub everything in here, I've got 3.46 times 10 to the negative 4. And then, you know, all of these are equilibrium concentrations, of course. So this would be Z squared over 0.184 minus Z. Now, if you look carefully, at that, what you can see is that you could actually solve for Z if you were willing to do the quadratic equation. So, you could take this out, you could distribute it, and you could end up with something that looked like AX squared plus BX plus C. And, you know, the quadratic formula for that, let's see, remember, let's go over here. And you can solve for x. X is going to equal negative b plus or minus square root of b squared minus 4ac all over 2a, right? You can do that if you wanted to. Now the thing is, though, that's pretty undesirable, I think. I don't think anybody wants to be doing that kind of math. So here's what we do. We look at the Ka value and we ask ourselves, well, is it a high value or a low value? You see, the thing is, if it's a weak acid, that means it doesn't dissociate very much, then I could make the assumption, we'll assume it's a weak acid. And if I do that, then 0.184 minus Z is going to be approximately 0.184. Okay, so what am I saying there? I'm saying there that 0.184 is Z is so small compared to 0.184 that we're effectively dealing with 0.184. And you might be wondering, well, how do I know I can do that? Well, I think as long as the Ka is less than, say, 10 to the negative 4, 10 to the negative 4 or less, it's worth a shot. It's worth a shot. And here's the thing. Now, as I've gotten older, I've got a bit of a problem with my eyesight, you see. And if ever I have a pizza, I can see the whole pizza here, but if somebody steals a piece that's less than 5%, less than 5% of the pizza, all I see is a whole pizza. That's terrible. Let's try that again. That's all I see. I still see a whole pizza. So you could steal some pizza from me and I'd never know. It's the same thing with the acids. As long as the dissociation is less than 5%, then you can say that the assumption is valid. You can say it works. So let's go ahead and do that. And then if we do that, then it's going to be z squared over 0.184, which is a whole lot easier to solve for z. And z then is going to be 0.00798. Now I want you all to try that in your calculator and see if you can solve for z. All right, try it in your calculator. Make sure you're getting that same z value as I am. Is
That's
anybody having trouble getting that?
3.46 to the negative 6
4.
power.
No, negative 4.
Okay. It looks like it's it.
All right,
Yeah, I
anybody?
got 0.007989724.
Oh, really?
Yeah,
Let me see that.
because you times
Well, let me see.
3.46 by 1.184, and then you square root it.
That's right. No, I get 0.007978, which would be 0.798, 0.00798. So my answer is correct here. It wouldn't be 0.00799. Alex, did you get that? So I'm not sure what happened in your calculator there, but something went amiss. All right, once you've got the z value, you have to see whether or not that value, which happens to represent, if you look at it, the value of H plus. I mean, those two things are the same. Then you will be able to see if the assumption was valid. So what you do is you take the z value and divide it by 0.184. You see the z and multiply it by 100%. You see, when you're doing percentages, it's always part divided by whole. So there's your part, which is the z, and there's your whole, which is the 0.184. So if I wanted to find the percentage of females who are on this call, I would add up all the females, sorry, just count all the females and then divide that by everybody in the room, part divided by whole, multiply by 100%. That'll give me the percentage. So likewise here, I can do Z divided by 0.184, part divided by the whole, and that will allow me to come up with 4.33%. So this will dissociate less than 5%, which means that the assumption was valid. And if it's valid, that means that, you know, we're fine. Now, what if it was invalid? What would you have to do then? Let's say it came out to be 7%. What would you do? What would you have to do then? Any
You have
ideas?
to like actually solve for Z properly.
Using what?
The quadratic method.
Yeah, using that quadratic equation.
That sucks.
Okay, so on the test, let me ask you this. What do you think the chances of getting a problem where it won't be valid, where the assumption won't be valid? What do you think the chance is?
Probably not very high.
Yeah, usually I get the answer less than 5%, but really the answer is 0. So no, you can expect that any problem you see will be one where it will be less than 5%. So you won't have to solve for Z in any other way. Now, once we get Z, then we can do the last part here, which involves finding the concentration of each species in solution. So there's one other step we need to make here. So the HCNO is 0.184 minus Z. And if we do the .00798, so if we do the math with the correct significant figures, we get 0.176. You see that the way that works is that we've got 3 places past the decimal here, so 3 dp, and here we've got 5 dp, 5 decimal places. So we end up getting 0.176, which is 3 places past the decimal. Does anybody have any questions? Now CNO minus and H3O plus are going to be the same, and they are going to equal Z, which is 0.00798. Does anybody have any questions? Anybody have any questions? All right. Let's take a look at the test here, and we'll see the kinds of problems that you would have to deal with for that. And it's going to be, let's see, I guess it would be 12, 13, and 14. So let's take a look at 12 first. It's asking what is the pH of a solution of 2.05 molar HA that has a Ka of 1.76 times 10 to the negative 5. So for this one, you know, you can work it out, obviously. And I'll just do it kind of rough over here. And I won't use the water. I'll just go HA gives H plus plus A minus. The initial is going to be 2.05. On the HA, and 0 and 0 on the other two. The equilibrium we've got 2.05 minus Z and Z and Z. All right, does anybody have any questions so far? So the equation we're solving for Ka is equal to H plus times A minus over HA. So I'll sub everything in, 1.76 times 10 to the negative 5 on the Ka. And then it's going to be Z squared over 2.05 minus Z. And then we make the assumption that 2.05 so we'll assume that 2.05 minus Z is approximately equal to 2.05. Now, the reason I can do that again is because my Ka is small. Ka is a measure of acidity. I mean, if it's a low value, it means it's not very acidic. As long as it's less than, say, 10 to the negative 4, 10 to the negative 4 or less, I think it's worth a shot here. So then we can solve for Z. And it's just going to be Z squared over 2.05. So Z comes out to be and I get 6.01 times 10 to the negative 3. And that happens to equal the concentration of H plus, but that's not what you're looking for. Look what you're looking for in a problem. You're looking for pH. So the pH is going to be the negative log of the hydrogen ion concentration, or negative log of H plus, which comes out to be, now remember you take the log and take the negative of that value, and I get 2.221. That's my final answer here. Now the number of sig figs we get here, we got 3 sig figs for the 6.01, and that means we need 3 places past the decimal. So 3 sig figs and 3 places past the decimal on the log. And that will give us 2.221. Does anybody have any questions about finding the pH? You're all okay with that, huh? Yeah, it's pretty brutal. There's only 6 of you here. 6 diehards. Now, I had trouble yesterday. For some reason, the lecture I was doing didn't record. I hope this one does. That's for sure. Otherwise, it's going to be a lot of people who are going to be upset. Okay, so I mean, if I was going to test the, if I was going to go ahead and test the assumption, I could. It would be 6.01 times 10 to the negative 3 divided by 2.05, and that will give me a percentage. Now, that's kind of what question 13 is asking for. It says calculate the percentage that allows for the deliberation of whether 1.63 minus H plus is approximately 1.63 in accordance with the 5% rule. So we've got a 1.63 molar solution of HA, and the Ka is 8.1 times 10 to the negative 5. I'm going to cheat a little bit here, And I'm just going to, change some stuff out. Because we do have to do the whole thing here. We have to solve for z. But you'll see it's going to be the same kind of process. So I'm going to go ahead and delete all that and we'll go from here. All right, so let's put this back in. So we've got 1.63 as being the HA concentration. And we've got 1.63 minus Z over here. And then it'll be 1.63 minus Z in the equation. And we're going to assume that 1.63 minus Z is approximately 1.63. And we're given the Ka is 8.19 times 10 to the negative 5 is Z squared over 1.63. And that means we can solve for Z then. Why don't you all try and solve for Z? Make sure you're getting the same answer as I am. I get 0.0116. Is everybody getting that?
Yeah, that's what I got.
Okay, good. Now the percentage that we're talking about here, so this is to validate the assumption. We do Z divided by 1.63. That's the part divided by the whole multiplied by 100%. So it'd be 0.0116 over 1.63 multiplied by 100%. And that comes out to be I get 0.007088. I multiply it by 100 and I get 0.709%. And that would be the answer I'd put in there. But I think it's just looking for I just think it's looking for 0.709. The only time you ever put in a unit in these problems is if it asked you for one. See, like in this example here, it gives you an answer, then it asks for a unit. Here, you're just looking for the numerical answer. Does anybody have any questions? Everybody's fine with that, huh? All right. Okay, the last one here is, again, we're doing pretty much exactly the same thing. We've got the concentration of H plus here, where it's actually been determined for us. In an initially 0.24 mole solution of HA, what's the new HA? Well, the new HA, let me get rid of that. Going back to the initial problem, this problem is actually not that hard. The new HA at equilibrium is going to be the HA initial minus Z. And the Z here is going to be what we're given, 0.24 minus 0.0100, which would be 0.23. So that's all it's after, is 0.23 molar is the answer. So the 0.23 goes in the answer box, and the big M goes in the units box. So the math has already been done for you as to figuring out the concentration of H plus in the solution. And then you know that the HA at equilibrium, let me write that down, right? HA at equilibrium is going to be HA, the initial, minus the Z. Yeah, from a picture point of view, it looks like this. This would be what it looks like initially. In solution, it looks like that. And then at equilibrium, you might get, say, one of these to break apart, especially if it's a weak acid. And then you know that the concentration of HA at the end is always going to be whatever you have initially minus the amount of H plus that you find you have. And that will give you the HAs that are left. So, you know, it's not really anything that's supposed to be too complicated. Does anybody have any questions? Does anybody have any questions? All right. Let's look at the very last part of this. I have to find my PowerPoint. There it is. Okay. The last part of this problem here. And what it's asking is, does H plus resulting from dissociation of water need to be considered? Okay, now this seems to be very, very complicated, but it really isn't. So when you've got a solution of HA, let me get my thing here. And you've got HA in water. There's actually the total H plus. I'll put water in here as well, just for kicks. But it's always dissolved in water. The total H, the total H plus is going to be the concentration of H plus from HA, which is fine. But we're also going to get a concentration of H plus from water as well. So we'll have a total H plus in the solution. But the thing is that the concentration of the H plus from the water is really small. It's a maximum, and that's why I've got it here as being listed as 4.5 times 10 to the negative 7 molar. That's really tiny. I mean, if you were to go ahead and write that out as a decimal, it would be that 0.00000045. I mean, come on, that's really tiny. So what we can say is that if the H plus from the HA is, say, greater than, we'll say greater than 10 to the negative 5, then the H plus from the water is negligible. Need not be considered. I don't know why this moved here. It seems to move of its own accord. Does anybody have any questions about that? So going back to the previous example, and I've got the answer here on the slide, you can see this. If H3O plus is 0.00798, which is what we got previously, I'll go back in the previous part of the problem. See, we got 0.00798 for the concentration of H plus. You can see that if I was to take 0.00798 and add it to 0.00000045, that my answer would still be 0.00798 once I took significant figures into account. Sorry about that. So you can see that the amount of H plus from the water didn't really affect anything. Now, conversely, if the H plus from the HA is less than 10 to the negative 5, I should say molar here, the H plus from the water would need to be considered. Now, I'm not asking you to actually do the calculation. I'm just asking you whether it needs to be considered or not. So you can see then if it's small enough, then the H plus from the water would matter. And that's really all I'm saying. Does anybody have any questions? Let's have a quick look at the test question here. And you can see these are the answers. This one says, given that the H plus from HA is 4.09 times 10 to the negative 9, and that the H2O, the H plus from water is 4.5 times 10 to the negative 7, effectively, does the H plus from the water need to be considered? Right, can anybody tell me what the answer would be here? Would it be yes or no to begin with? Would you have to consider the H plus from the water? Yes or no?
Yes.
Yeah, and the answer is yes. And just because if you look at it, it says the H plus from the HA is less than 10 to the negative 5. In fact, it's 4.09 times 10 to the negative 9, which means that it's so small that when you added these together, the 4.5 times 10 to the negative 7 would matter. I mean, you can try it in your calculator if you don't believe me, but it would matter. So the answer would be yes. And so it's going to be one of these. And it's because the H plus from the acid is far less than the H plus from the water. If added together, significant figures, the H plus from the acid would be affected by the H plus from the water. So that would be the answer to that. Does anybody have any questions? All right, so in this question, you're either going to get a big number here or a little number. And this one here happens to be a little number. So you just have to be aware of what you're doing with it. All right, well, that's it for today. Does anybody have any questions, last minute questions? If you want to hang around for a little bit, you can. I do have lab at 9:30 though. I'm hoping this recorded because a lot of people didn't turn up today. All right, well, I'll see you all later. Thanks for coming.
Have a good day.
See you in a bit.
Bye.
There's it.
Bye-bye. Thank you.
Bye, thank you.
You're welcome.
And I'm going to be missing lab, but I'm pretty sure I'm fairly ahead on lab.
Okay, fair enough. No worries.
Yeah, I'm pretty sure you know that too, though.
No, it's okay. No, it is optional, Sondus. You know, I don't push it. I don't think negatively of anybody who doesn't come. I just think that they're doing it on their own. They're okay.
All right, thank you. I appreciate it.
No worries. I'll see you later.
All right, bye-bye.